Hello again and welcome back to my channel. Today we'll talk about text retrieval embeddings, such as E5. So we'll talk about how to train them, what is contrastive loss, what is knowledge distillation, and in the second part of the video we're going to read the source code for pre-training of such a model. So here's the plan for today. As usual, I'll start with some introduction of what that actually is, where the model stands compared to other models, and how to navigate in the entire field. So I'll talk about what are retrieval embeddings, what different transformers there currently are, such as ChatGPT and E5 embeddings and BERTs, about Bert Architecture in particular, about the difference between cross-encoders and Bi-Encoders, and then we'll talk about the actual training. So contrastive loss, what is negatives and hard negatives, knowledge distillation, and the final part, probably the biggest, code reading. So first, what are retrieval embeddings? And we can describe them as something that allows you to answer a question using a large database of text. So let's say you have a question and then you go into that database. It might have billions, trillions of documents, and then you retrieve top 100 that might be relevant to your question. So for example, you might have a question like, what did the success of Manhattan Project mean? And you will have a lot of documents. Some of them might be quite relevant, like this one saying that the success meant blah, 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 or something that kind of looks similar, but not really relevant. So this one is about Manhattan as in the place in New York. And so it's definitely not relevant. And some of them might be completely relevant, and you still have them in the database because your database maybe was designed to answer all sorts of questions. And so the goal of retrieval embeddings is to search through all of that and find some relevant answers. And so the main difference to other models such as ChatGPT or BERT is that we want to make it effective. We want it to scale. And to do that, we basically will encode the query and all the documents separately into an embedding, and then use some neighbors engines like Qgrant or Vesp or something like that to actually search through these embeddings. And this is the paper that we're talking about today. So it presents E5 retrieval embeddings. I want to say that the idea of retrieval embeddings is quite old, because the alternative is to look for just bare text, and computers are not really good at processing bare text. And so people wanted to come up with this easy to use scheme for searching through large corpus of texts. And so Google had this idea of Word2Vec, for example, maybe 15 years ago, but it didn't quite take off, as in it couldn't really beat some simple baselines like BM25 until transformers came along. And E5 retrieval embeddings are actually the first of the kind that beat that easy baseline of BM25. Another thing I wanted to show you is this MTEB leaderboard on Hugging Face. So this is the collection of different retrieval embeddings and their comparison, just to give you a quick overview of what we have at the moment. And so you also will want to look at the model size and embedding dimensions when comparing the model, because model size basically affects how much compute you need to spend to create your database. So we're not going to use that every time someone asks a question, but you still have this database. You might want to update it from time to time. You might want to add new entries. So for a search engine like Google, that's actually a lot. Like if you have 1 trillion documents and 1 billion appears every day, you need a lot of compute if you want to use this big model. And then the second thing to look at is embedding dimension, because now it costs memory. So if you have 4x embedding dimension, you would need 4x memory to store that, and that's also might be expensive. And so we can see at the very top here that all the models like this Qwen7b instruct with 7 billion parameters. That's basically an LLM. So it's a huge model, quite a lot of compute needed. The embedding itself is also huge. That's why they are at the top. We also have some more modest models like currently probably the best along the smaller ones is Gene Embeddings with 3, with 500 mil parameters, 1024 dimension embedding, GTE large, slightly smaller model, again, same embedding dimension, BGE large, again, slightly small model, 1024 embedding dimension. All of these I actually hope to cover on my channel in the future. And then way down below here, we actually have the first one that is called E5. So it's an older model. It's maybe not as good as the modern alternatives, but it helps you to understand the basics. So this is what we're talking about today. Next, let's talk about transformers taxonomy and what different models there currently are in the field. And so the first big category is decoder only. And these are the models such as GPT, Llama, Claude, and so on. And so their main distinction is that they have causal attention mask, which means that they do next token prediction. And this is basically what lets them generate text. So in layman terms, you can talk to the model. You can ask ChatGPT, please help me, and it will actually type you the answer. Another big family of models is encoder only, such as Bert, E5, BGE large that we've seen from the leaderboard in MTEB. So now the core distinction is that they have bidirectional attention. So when interpreting the token in a sentence, they allow to look backwards in time as well as forwards in time to understand what it means, which basically means that they cannot do next token prediction. What they use instead is masked token prediction, or MLM, where they try to, so in the input, they mask out some of the tokens and then they let the model predict what the masked token was. And the bad thing about that is now we cannot talk to the model, we cannot use it to generate text, and we instead do some more old school stuff like classification, regression, all of that. The good thing about that is that bidirectional attention is, it gives more information to the model. So with this, despite not being able to generate text, you can actually get out some accurate predictions from this model, even for relatively low sizes. And then the final one, encoder decoder, the only actual model that does that I heard about is T5. So it was quite popular maybe 5 years ago, when this whole Bert and GPT thing were just coming out. So what it basically does is it has some prefix with bidirectional attention and then suffix with causal attention. So it allows it to maybe answer questions where you use bidirectional attention for the question, so you understand more of it, and then you use next token prediction to generate the answer. So again, these models can be relatively small and you can still use them for text generation, but I haven't really seen any of them being used in production. Maybe it's just me. Another useful way to look at that is what different model sizes there are. So GPT-1 had 100 million parameters. So in our comparison, that's a tiny dot over here. Then GPT-2, 1.5 billion. Now that's quite significant. Llama 7B, for example, that's 7B of parameters. GPT-3, I think, had about 150 billion parameters, so that's much more than all the previous combined. Llama, the biggest models of Llama family have 400 billion parameters. Again, that's huge. GPT-4, I think about 1 trillion, so that's again much more than the previous models. So if you want to ask a question, you're not going to ask it to GPT-3 or GPT 3.5 because you know you will get incorrect answer. So for this text generation, you basically need this huge model. So 1 trillion parameters means that you cannot do inference on your laptop. You cannot do it on like an H100 node. You need an actual cluster that costs a lot of money just to store the model, just to do the inference. So all of that is quite expensive. That is why OpenAI company needs so much money. And if we compare it to our BERT models, so E5 large, that's about 300 million. Again, tiny dot compared to other models here. The biggest we've seen for retrieval. 7 billion. Again, not that much. So E5 large actually inherits from Bert large, which also had about 300 million parameters. Again, a tiny dot by VE standards. So thanks to this bidirectional attention, these relatively small models can still deliver some value thanks to the fact that they can use more information from the input text. So a quick clarification about the connection between E5 and other retrieval embeddings and Bert. So first of all, E5 uses Bert Architecture, so it's exactly the same model. In fact, later on we'll be looking at the code. The actual inference is done using Hugging Face Transformers library, and E5 is actually represented by just Bert in that classification. And another thing is that when we train retrieval embeddings, we actually start with weights, pre-trained weights of Bert. So we do not train the model from scratch. Instead, we take the Bert, which was trained on this masked language modeling and on some sort of classification task, and we take that as a base model and then fine-tune it for our retrieval task. Now let's quickly review the architecture of Bert. So let's start with some text. So we have this text with some special tokens added. So CLS, as we'll see a bit later, is a special token that allows you to output something on sentence level, like classification or retrieval. Then we have first part of this text. So in this case, this is a title. And then we have this special separation token, and then the text of the document. And the goal of this separation token is to distinguish different parts of the input text. So that might be title and the main content. It might be question and the answer. Next, what we do is we tokenize that. So we represent these words as integers. In addition, we use these input separation token to understand which token types there are. So in this case, we have two token type IDs. So the first part of the sentence, the title, will be represented as token type 0, and the main content of the text will be represented as token type 1. And in addition to that, we always have positional encoding. So we basically know the position of every token, and we also encode that in the model. So how exactly we encode that? We encode that using so-called embedding lookup. That is, for each number, for each unique number, we look up an embedding row from some sort of matrix, and then we just sum all three of these together. So we add embeddings from token ID, from token type ID, and from position ID. We just sum them up and then pass them to the transformer. So this is how they are represented in transformer. This is a tensor of length, sequence lengths, the number of tokens in the input, times, let's say, 768 embedding dimension. Then we pass all of that through the actual transformer. Again, this is a Bert model, so it has bidirectional attention, which means that each token is allowed to attend to tokens to the left as well as to the right. So in GPT, for comparison, each token is only allowed to attend to tokens to the left. So this is the causal attention. The output of the transformer will be a tensor of exactly the same shape and roughly the same meaning. So we can say that this token basically represents this input word. And in fact, this embedding output, we can add a classification head on top of that. And since it was trained to solve masked language modeling, so it will predict what token that is, it can actually say that, yeah, this is the token named project. And then this first token that corresponds to CLS token, in many cases is used to output some sort of sentence level information. For example, the score or classification for the entire sentence. Now let me explain the difference between cross-encoders and Bi-Encoders. So a cross-encoder, sometimes also called a re-ranker, is when we need to answer a question, and we take that question, we concatenate it to the text of the document using the separation token, and then we pass that through the model. So what that gives us is that we have this question, we have this text of the document, and when the model interprets the text of the document, it already knows the question. So we can actually compute the attention between text of the document and each of the tokens in the question, which lets us interpret the document text more easily. And so then the output of the CLS token is used as some sort of score for current document for a given question, and we can rank different documents by this score. The higher score, the better. Now, Bi-Encoders separate question and text. So now we will pass only the question through the model, and we will take this CLS token output without projecting it down to a single number or classification head. We'll just take the actual embedding, and this is our new representation of the question. And we'll do the same for the document. So we'll pass the text of the document through the transformer, get some sort of embedding. Now you can see just how much more difficult this task is, because now what we do in this right part basically is that we need to store so much information about the text, not knowing what will be asked of us. We need to prepare ourselves for all possible questions. So we need to save as much as possible in this small embedding, so that when we got the question, we can already answer it without having access to the initial text. So this part of the model is sometimes called bottleneck because of that, because we're basically asked to write a tiny helper for ourselves that will allow us to answer all sorts of questions for this text. And so then how these embeddings are used is that we compute some sort of similarity metrics between embedding of the query and embedding of the document, for example, cosine similarity, and then we use that cosine similarity as a score to rank these documents. Okay, so how do you actually train these Bi-Encoders? And the first component of that is contrastive loss. So forgive me my image examples now, I used them to make the explanation simpler, but we were still talking about text models, although similar concepts can be used for images as well. So we have some sort of query, and then we have some positive example, so something that answers the question, and we have some negative examples. So the query was about the dog, and the positive is a dog, and then negatives is a cat, a fish, a monkey. And so we can represent them in some sort of embedding space, and so we want this positive example to be pulled towards this point here, and then we want the negative examples to be pulled away from it with our loss. So a couple of clarifications for this visualization. So first of all, this dotted line here underlines the fact that we're not just putting the query here. Instead, this purple dot represents the document that is the most similar to the query. And metric of similarity in our case is supposed to represent how well the document answers the question. And so it's not the same as being exactly like the question. So just repeating the question is not actually answering the question. So this is a huge distinction. And so this projection here means that we have this question, let's find the document that answers the question. So that's first distinction. Second distinction is that our embedding space is actually multi-dimensional. So we had 784 dimensions, and that basically allows us to put different things closer or further away from each other on different coordinates. So for example, if you ask what is the most similar to the dog, then obviously the dog will be more similar than the cat or a fish. But then if you ask something like, what did John Smith had as a pet in childhood? So maybe he had a dog and a monkey, but no fishes or cats. And so when we are asked this question, suddenly in some coordinates we'll see that the dog is more similar to the monkey than to the fish or a cat, for example. So that's why we need many dimensions to represent all this sort of information, and the similarity between the question and the document actually shows how relevant it is. And this is the actual equation for contrastive loss, so L-cont contrastive loss. So this term here says that we have the exponent of some sort of similarity metric between query and positive example, and then in the denominator we have similarity between query and positive example plus sum of similarities between the query and some negative examples. And so similarity can be a cosine distance between embeddings, for example, and it is divided by this temperature. So you can look at it and say that this term here increases if we increase the similarity, and it decreases when we increase the similarity of this negative here. And since we have this minus sign here, we need to minimize the loss to increase similarity between positive and decrease similarity between negatives. A couple of words about this temperature parameter here. So there's actually an entire paper explaining what that is and how you can visualize that. And so, for example, here they have a cool visualization of how you might represent embeddings for different temperatures. So for higher temperature, you can see that the points are sort of more clamped together. And so for example, with extreme temperature, you might see that all high-level concepts like animals and plants and objects, they are all clamped together in this one spot, and there is no distinction within the group. And then with the lower temperature, you start distinguishing between animals of different kind, so maybe cats and dogs, and then with even lower temperature you start distinguishing between different breeds of dog and cat and so on. And in some cases, when you decrease the temperature too much, you might see that you actually break the semantic meaning. So for example, you start giving different meaning to just different synonyms of the same word. At this point, it becomes too spread out, I would say. And so this is a hyperparameter, so in the actual training you want to try to tune it, so there is no way to say ahead of time which temperature you need. But this paper in general, I will leave the link in the description. This paper explains how you can think of contrastive loss in general. Now let's talk about negatives and hard negatives. So first of all, how do we prepare an example for training? We need a query, we need positive or a few positive documents, and we also need some negatives. And so you might start with something like labeled examples. That might be something that was shown to the users and the users clicked or not. That might be something that you've shown to special assessors and they determined whether or not it's a relevant document. In either case, the problem is that the actual database is much larger than that. And so all the labeled examples that we have here represent only a small portion of the database. And the golden rule of machine learning is to train your models on the same data distribution as you'd have when you perform the inference. And in our case, the inference will have to be performed over the entire database, which includes all of these examples that are there in the database that are not really connected to the current question. And so you need that data distribution in your training. And another problem with that is accuracy. So let's say that your model has 99.9% accuracy. That is 1 in 1,000 errors, right? And let's say you have 1 billion documents in your database. So now if you apply the model to every document, even this 1 in 1,000 errors will yield 1 million errors that you fetched from this database. And the actual answer to the question might be contained in just one document. And so your retrieval quality is not that great because you've just retrieved 1 million errors and one relevant document. And so this is a huge problem to be aware of. And so coming back to our question of negatives, the first most logical thing to do is to just fetch random documents from this database. And this will represent your data distribution that you have. One of the ways to mine such examples is to just take a look at your batch. So in your training, you will have batch gradient descent, and in a batch you have random queries, and you can say that for the current query, let's look at neighboring queries within the same batch. So they were sampled randomly. So a random query, if you have enough queries, is most likely not connected to the current query at all. And so the positive examples for this query are going to be negative for the neighboring queries. And so you can use that as your negatives. And so if you think about that, the data distribution of these in-batch negatives is actually going to be close to that of your random documents from base. With these random negatives, the problem now can be that they're too easy. So for example, we have a query like that, a positive example like that, and then a negative from which it is completely obvious that it's just a random document from base. So we still need those to actually make the model aware of those, to prepare the model for all the data distribution that it will meet during inference. But these examples might actually become too easy too quickly during training, and so we need something better. And what we can do is we can mine hard negatives. So in the original E5 paper, they started with BM25 hard negatives. So BM25 is a simple scoring function for text, where we basically look at frequencies of the words in the text and overall how frequent that term is. So we downgrade the really frequent words and we pay more attention to rare words and just do a simple scoring function across the actual words in the text. And so we've talked that it's a potential baseline for retrieval, but we can also use that in mining our hard negatives. So now in our picture here, we see the entire database. In batch negatives, we see this small subsample of examples for which we have labels, and then a quite larger sample, but closer to actually hard negatives with BM25 hard negatives. And then after that stage, you might go even further and say that, okay, my previous generation of the model will be used to mine new hard negatives. And these are called mined hard negatives. So now we are even closer to our labeled examples. The examples are now even harder, and that helps you make the model even better. And if we go to the actual GitHub repository for pre-training of this series of models from Microsoft, they actually repeat this process several times. So they start with BM25 hard negatives, they train retriever, then the mine more negatives, train another retriever, and then they actually use that to train a re-ranker cross-encoder, and then use that cross-encoder in knowledge distillation, about which we'll talk in a bit. Now let's talk about knowledge distillation. So the problem with just contrastive loss was that we now have different sorts of negatives. So we have labeled examples that might really look like something relevant. We might have random documents from base, which are completely irrelevant. We might have something intermediate like BM25 hard negatives. There isn't really a way to represent their differences. And this is what knowledge distillation is used for. So the idea of knowledge distillation is that we have some sort of teacher model, and that teacher model can say that, this example that used to be just positive is now represented by some sort of score like 0.83. And then this example that was negative before, so it's 0, it's now 0.78. So although it's negative, it's really close to the score of a positive. And then this example is 0.01. So this is something completely far from what we want. So this is the idea, to make our grade more smooth. Now the question is like, where do we get the teacher? And one of the answers is to just use cross-encoder. So cross-encoder has query within its context when it tries to understand the text, and just that gives the model a lot of advantage, so it can generate these scores much more easily than our retrieval model. Another way to do the same is to just get a much bigger model, maybe even an LLM, because we just need it for training. We're not going to use that for every request in our service. We're not going to use for every new document in the database. So we're less constrained by the size of the model. And then to train that, we use divergence loss. So this is how it looks like, and it basically says that we need to make the predicted probability as close as possible to true probability. And this formula here actually looks a lot like cross entropy, and divergence can be seen as a variant of cross entropy loss. So in cross entropy loss, we had a set of classes like 0 and 1, for example, and then we predict some probabilities. And here we have basically two sets of probabilities. So we have a teacher model that predicts one set of probabilities and our model that we train, and we want the predictions of our model to converge to that of the teacher model. Now let's read the code of the model. So the code can be found in this GitHub Microsoft unilm repository that we've seen being linked to in the paper. So this repository has a bunch of models by Microsoft, and one of them is called E5, but unfortunately this variant of E5 only has evaluation scripts. It doesn't have pre-training, although somewhere, I believe in the GitHub issues here, the developers from Microsoft actually said that for E5 pre-training, just look at SimLM code. So this is what we need. So this is the unilm/SimLM repository, and they contain this blueprint of how to do pre-training for contrastive loss, for knowledge distillation. They also have a bunch of things for the actual re-ranker training and so on. So as usual, I download the repo, I install it. I'm going to leave all the instructions in the description, and they have instructions to reproduce in this repo as well. And so for Bi-Encoder training, they say to download the dataset, which is MS Marco in this case, and then launch this train Bi-Encoder marco.sh. So let's take a look at this one. So this is how it looks like. It uses this thing called deep speed. Not sure what that is, but it's basically an analog of torch run, which is a program to run several Python scripts in parallel on one machine. And what it allows you to do is to have cross-device parallelism. So it's just one node, so it's not cross-node parallelism, but if you have 8 GPUs on a same machine, you can use torch run or deep speed to use all of these GPUs to do training. And the actual script being launched here is src/train Bi-Encoder.py. So let's take a quick look at that. So it's there's not too much code in here, so we can notice here that they use this Hugging Face argument parser. They initialize the model, they initialize the trainer. So if we go to this trainer, we can see that it inherits from a thing called transformers.trainer. So it's a Hugging Face library. We can Google it. We can say Hugging Face trainer, and it will tell you what that is, how to use that, and it's relatively simple. So basically, this thing is used to hide all the complexity of training from you. So they've already written code on how to do actual batch gradient descent and all the little details that we don't usually discuss, but that are actually really important, such as automatic mixed precision, gradient clamping, learning rate scheduling, and all of that. So all of that is already implemented in the base trainer class. And what you need to do is to basically create your own class that inherits from that. And the only thing that you actually override is this compute loss function, which basically calls the model and tells what loss to compute. So to explain all of that better, as usual, I have my Jupyter notebook, which is placed at the root of the repository, which allows me to just copy paste the code from this Bi-Encoder train Bi-Encoder.py script. And also I've launched it once in the debugger to copy all the arguments being passed around. And so I just save them to sys.argv and use this Hugging Face argument parser, which allows me to use all the same objects as they do in their Python script. So then we just basically repeat the same process. So we have model, tokenizer, data collator, which is the thing that unites several examples from the data set into a single batch, and so on and so forth. And dataloader and Bi-Encoder training. So then train dataset is a torch dataset, so we can index into it using the square brackets and get the first example and just print out what's in there. So yeah, what's an example? It's a dictionary with a bunch of basically tokenized text. So we have Q input ID. So once again, example is just a single query, one positive and several negatives. So Q input ID, that stands for the tokens of the query, and we have 16 of them, and this is how they look like. Then we have D input IDs, which is now a 2D array with length of 16, which is a coincidence, but this stands for one positive and 15 negatives, and we can print the actual sequence length of all of those, and they all will be different. And it's this model is just a transformers model, and it uses transformers tokenizer, which means that we can initialize a tokenizer like that and call this tokenizer.decode method to actually see what those tokens mean. And so this is the question, which says CLS, some stray token here, and then what was the immediate impact of the success of Manhattan project. And then for different documents, we see the actual text of the document. And so here we have title of that, and then the presence of communications and so on and so forth. The only cloud hanging over the impressive achievement is what their success truly meant, hundreds of thousands of innocent lives obliterated. So this one actually seems to answer the question. So this is the positive. And then second example is no title. Was the New Deal a success? One, whether the New Deal was success or not depends on the definition of success. So now this talks about the New Deal, which is an economic policy. It has nothing to do with Manhattan project. Next document is what is the distance between Manhattan and Kabul, then Manhattan apartments for rent, and so on. So this is, I remind you, they start with mined BM25 hard negatives. So you can sort of see how BM25 works. So the question had something about Manhattan, and so the mined examples with a high score of BM25 will contain these words, but used in a completely different meaning. And so this is what we train the first iteration of the model. So then we can initialize the dataloader and fetch the first batch from the dataloader like that. So now batch is several questions, several examples united. And so for that, we basically just need to add padding to make sure that different sequence lengths are now represented as a single tensor. And we can see here that now we have 16 queries in a batch. Inside this Bi-Encoder trainer, we actually unpack that into a query batch dict and doc batch dict. So then we have to deal with this device parallelism. So normally we want to train on several GPUs located on the same machine. We don't want that for debugging. And so the way to make all of that work is to write a simple function with torch distributed that just says that I'm actually just launching this process group with world size of 1, which means that there's going to be only one process there, and the current rank of the process is 0, which means that there we'll see some so-called breakpoints in the code where we need to wait for other processes, and they will basically say that, well, I've just done a forward pass, I've computed the gradient, now we need to wait for other processes and exchange gradients. Well, in our case, there is no other processes, so we just sort of skip through that and continue. And I need this distributed mode like this. And then we can actually call the model. So I execute this code and I get out the outputs. So let's see how they look like. So they have this QReps and PReps. So QReps is basically embeddings of queries. So we have batch size of 16, and for each of the 16 queries, I have just one final token embedding per query, which is of dimensions 768. And then the same for PReps. P stands for passage. So now we had 1 positive and 15 negatives and 16 examples in a batch. So that's 16 times 16, that's 256 examples with the same batch dimension. So then we have the trainer. So the trainer calls this compute loss function on this model and a batch. So if we look into this, it's actually really simple. It just says that I call the model and I print out some metrics. So the actual loss is going to be a part of the model here. So model code is what we need to read. So let's see what the model is. So it's a Bi-Encoder model, and we can find it over here. Let's see what that is. So it's a Bi-Encoder model. It inherits from nn.module, and so we need this forward method. And let's just put a breakpoint in here. And then I can sort of repeat the same cell. This time I press this debug cell command. And here we are at this very beginning of forward method of our model. So let me just validate how the input looks like. So we have a query and passage, which is a dictionary from basically IDs, token type IDs, and attention mask. So attention mask has zeros for those tokens that just belong to padding. Then for queries, token type IDs are always the same. And for the document, we sometimes have zeros and ones. So I believe zeros for the title, which is empty sometimes, and for the padding, which doesn't really matter, and sometimes for the main content of the document, let me just print the entire first document, for example. So we have short title, then the main content, which will have ones, and then we have zeros again for padding. So these first set of zeros and ones basically lets us encode different parts of information inside inside the text. So the first one is title, which is really short and descriptive, and then the content, which is long and contains a lot of information, and so on. So then we have this compute scores function. So let's go to that one, and basically calls this self.encode function for query and for passage. And so this one is for query, I believe. And then the encoder, which was defined here as LMQ, and we also have LMP, this is just the Bert model. So Bert model is not defined in this repo. In fact, as I've told you, this is exactly the model from Transformers library, and we are not going to read that code today. Instead, I'll refer you to my previous video that actually reads the source code of this Bert model. Here we'll just sort of skip through that, and I will leave the link to the video in the description. And so this is how we gather the input for the models. We basically iterate over all the dictionary items except knowledge distillation labels, which we don't have at the moment, and then we get the outputs. So let's print out how they look like. So outputs might contain all the intermediate layers as well. We are interested in this last hidden state, so this output of the final layer of the model. And so it has 16 tokens, 16 batch size, and then for every token this huge embedding. Then we do what is called pooling, which means that we need to combine these tokens into a single embedding somehow. And there are different ways of doing that. Two most common would be to gather the first token, which corresponds to CLS token, or just compute the mean of all of them. So in this case, we do this first token one. So for every element in a batch, index into this second dimension and take the first token of that. So this embeds object is now going to be of shapes 16 by 768. So one embedding per query now. And then we have this self.puller in addition to that, which is just identity, so it's not really doing anything. And then we do normalization and we return. So this embeds.contiguous doesn't really change anything. It just makes sure that the index, the tensor that you've just indexed into, will be sort of restructured in memory to make sure that this embeds object now contains a single array in the same memory spot to make everything quicker. So we return from this encode function. So we get qreps, preps. Let's just continue to here. Let me print out the result of preps as well. So now we have 256 total documents, 16 positives and negatives for each of the 16 queries. Then we have a bit of distributed processing synchronization steps. So normally we would either have model parallelism or data parallelism. So data parallelism is when we have a batch of examples and then we send a small part of that batch to every device. And this is what will happen right now. Model parallelism is when we, instead of splitting the batch, we split the actual model. And the benefit of that is that now we can train huge models, and that's what is usually used in LLMs. In our case, we copy the model across all devices, so we're quite limited by GPU memory, but we train faster because we process the input examples in parallel. So normally with data parallelism, the only point in synchronization that you would need is when you compute the gradients. So you do the forward pass completely on your own, you compute the loss, you compute the gradients, and then you have to exchange those gradients with other devices. In our case, we use what is called in-batch negatives. And for in-batch negatives, we're actually interested in increasing this effective batch size because we get more examples that way. We get random positives from different queries as negatives for our current example, and know that this is happening in addition to BM25 mintar negatives. Basically this effective batch size needs to be large enough so that we can gather all sorts of negatives examples from neighboring queries. And for that, we sort of do a slight change to this data parallel algorithm, where we now synchronize before computing the loss to get all the positive and negative examples from other devices, to get the in-batch negatives, and then we split again into several groups so that we compute the gradients only for our examples. So this is what happens here. So first we've computed this representation of query and passage. So this is the forward pass of the model for our device. And then we synchronize across devices. Then we have this function called full contrastive scores and labels, which is actually going to deal with creating the labels and mining these in-batch negatives. So let's go to there. So here we create the actual labels, and also we multiply query and document scores between each other using this torch.matrix multiplication to get the score for the pair, right? So let's print the shape of that one and then think about that for a little bit. So the shape is 16 by 256. So we basically have one query, for each query, 1 positive and 15 negatives, 16 in total. And then we have 16 queries in a batch. And in addition to 15 negatives that we've got within that query, we're also going to look at all the neighboring queries, all the examples that we have for them, positives and negatives, and also add them as negatives. So that's 240 in total from other queries, or 256 in total. So for every query, have 256 examples, 1 positive, 255 negatives. And the labels say that they basically encode the index of the example that is supposed to be positive. So for first query, that's example number 0. For the second query, example 16, and so on. And sometimes we don't stop there, and we go a bit further, and we say that, let me just continue first and then explain. We also say that let's actually multiply query to query, and then positives to positives, and then query to positives again for neighboring queries, and say that that's negatives as well. So QQ, that's going to be an object of shape 16 by 16. So we say that for a given query, all the neighboring queries in a batch we consider as negatives, and then QQ, KK is the same for positives. So each single positive for this query, positives for neighboring queries are going to be negatives, which is completely different to what we had here, right? So here we always multiplied query embedding by document embedding, and here we sort of multiply query embedding to embedding of other query, and then document embedding to embedding of other documents. This KQ is again 16 by 16. I'm not sure what the difference to this first one is, but yeah, we add that as well. And then we concatenate all of that into a single tensor. So the shape of that will be 16 by 304. So that's 256 in batch negatives, plus 16 query to query, 16 document to document, and 16 document to query again. And I remind you, labels still encode the location, the index of the positive, and they end at 240, which means that all of these extra objects that we add here, so query to query, document to document, they're all going to be negatives because there's no index to say that they are positive. So then we return from this function. So this is a small part that actually deals with the temperature, and it might also have this temperature warm-up thingy, and this is how we basically provide this temperature to the loss as a scale, and then we multiply the scores by the scale, right? And then we have this index select. So to perform the in-batch negatives, we had to synchronize and aggregate batches from other devices. Now we want to desynchronize again. We want to select only those parts that belong to our batch in order to not repeat the same calculation of gradients. And that is what we do here. And that's what is being returned from this compute scores function. And let's return from that one as well. And the last part here is the actual loss. So we have some code for knowledge distillation, not in this case. So again, not knowledge distillation. And so we just call the loss. I've told you it's called contrastive loss. Well, here it's just called cross entropy. So it's PyTorch cross entropy loss. And we have all scores and all labels. So all scores is this object of 16 by 304. So 256 16 original negatives, then 256 total and batch negatives, and then 48 extra negatives. And then all labels just encodes which of them are positives. And this is the cross entropy loss. So cross entropy loss says that for the first query, the score of element number 0 needs to be 1, and of all the other elements needs to be 0. So all scores for the first query, this is how they look like, right? And we want basically this element to go up, not necessarily to 1 because we have softmax, but basically to go up. And then all of these other elements need to go down. And this is our contrastive loss. Next, I also want to show a bit of code regarding knowledge distillation. So once again, in this unilm repo, they have an example of how to launch the training like that with a slightly different script, train knowledge distillation Bi-Encoder.sh, which roughly calls all the same code but with different arguments. And so here I have a second Jupyter notebook, again roughly the same, different arguments. And so let me just point out what is different. So again, we initialize the model, the dataset, the dataloader. I fetch an example from the dataset. And so one difference now is that we have these KD labels, knowledge distillation labels, and this is how they look like. So again, first element is always going to be a positive and everything else is negative. And you can see that the score of this one is the highest, and for everyone else it's lower but different to each other. And then we have 24 examples, 24 documents in a batch. And we can take a look at them, right? So it's still the same example, the first one from MS Marco. So the first one is the positive, which is the same one we've read before, which says about, the actual result of the success of this project. And now another detail is that now we go from BM25 negatives to mined hard negatives as top documents retrieved by the previous model. And you can see that we get basically everything now talks about Manhattan project. So they don't talk about Manhattan, the area in New York. They don't talk about the New Deal. Most of them talk about the actual Manhattan project. So the model is smarter. We can see it in the examples here. But if we read this text, it's not actually answering the question. So let's read example number 6 and 7, for example. So 6 actually is completely about a different thing. So this one talks about planet Neptune, and then the 7th example talks about the Manhattan Project. And you can read this, talks about lack of communication, military, laboratory led to devastating moral disasters of the 20th century. So it talks about the Manhattan Project, but not about the actual result and the impact of that. So it's still a negative. And if we look at knowledge distillation labels, so label number 6 is probably the smallest in this batch in this example, so minus 6.8, which talks about Neptune. And then the next label talks about Manhattan Project, but doesn't really answer the question. That's slightly higher, minus 3.6. So this is how cross-encoder basically allows us to treat different examples differently. So then we have all the same stuff. So dataloader, initialization of the process group, and the model. So now we come back to the same code that we've just read, and this time it is supposed to be about knowledge distillation. So let me press this debug cell here, and here we are. So now we go into this branch with contrastive loss. So again, we have scores, we have targets that we get from these KD labels, and for the actual loss we use this Kyle divergence loss. So it's torch Kyle div loss. This is it. This is the actual formula for the loss, and we passing these group log scores. So 16 queries and 24 examples per query. So for this one, we basically selected only those indices that actually belong to this query. So we're not doing in-batch negatives now because we don't have knowledge distillation labels for them. So we only have 24 examples for every query, and that's what we pass to this Kyle divergence loss. And the target is basically just the actual labels that we got in the dataset. Again, the same shape. And so Kyle divergence loss will try to basically make sure that the scores roughly correspond to the target. So it's kind of like regression really, but with slightly different meaning behind that. And so this is it for today. Thank you everyone. I hope that answers the question. I hope that was interesting, and see you next time.